So, we've learned about the heat equation and how we can figure out how much heat is needed to heat something up. So this equation, heat energy is equal to the mass times the specific heat of the material times the change in temperature. This only works when the change is only how to word that. So this only works when the change only includes a change in temperature. Recall that temperature is the average kinetic energy of the motion of the molecular particles. Does any other changes occur when you heat things up? I mean, sometimes, but we're only looking at one substance. We'll assume the substance doesn't change. Are you sure?
Well,
You can give this to Buddy.
So the heat changes when you heat something up?
Yes, but what else changes? What's a think of a chemical or a substance. Water. Now, what happens if you continually heat up water? It doesn't evaporate, it boils. So what's it doing? It's boiling. It's turning into a situation where the molecules are loosely bounded to each other. So these molecules are slightly bonded to each other. They're not bonded too well, to a situation where they're free to move around in space. So they can move in random directions. These have some molecular forces that limits their motion. While when it turns into a gas, it's able to move more freely. We also have the situation where it's an ice. When it's an ice, it forms a crystal where one hydrogen bonds to the oxygen of another, and this bond completely limits the movement of these atoms. So, let me ask you this question. When you're boiling water, what happens to temperature?
Well, now it stays the same.
Stays the same. If you were to take ice, so let's say that we start out with negative 10 degrees Celsius ice. So let me plot this. We have temperature on this axis, and we have time on this axis. So let's say that it starts at negative 10 degrees Celsius, and you start heating it up. What's it going to do? It's going to raise in temperature until it reaches 0 degrees Celsius. Once it reaches 0 degrees Celsius, it begins melting. But when it melts, the temperature doesn't change. So this is during the melting. And then once it's all liquid, it begins heating up until it reaches 100 degrees Celsius. At which point it stops heating up until it's all gas. And then it begins heating up to temperatures over 100. So this will be the boiling phase change. So here is a solid, here is a liquid, and here it's a gas. So if we're constantly putting in the same amount of energy into the system, where does that energy go? when it's a liquid, when we're heating up liquid water, that energy is going into increasing the vibrations of the water molecules. They're bouncing around faster and faster, sliding past each other and moving until it gets to 100 degrees Celsius. At which point, the temperature does not change. So what's going on? Where's all the energy we're pumping into the system going? So during a phase change, so remember what I said heat is. So temperature is a measure of average kinetic energy. And what did I say heat was a measure of?
The transfer of energy from one object to another.
And I wrote later on top of it, I wrote something else.
The total.
Total energy. So heat is a measure of kinetic energy plus potential energy. So temperature is the kinetic energy portion. So temperature is this, kinetic energy. If we were to plot this, we see during boiling, the temperature isn't moving. So where's all the energy going into?
It's just
Potential. So what we're doing is we're increasing the potential energy of every molecule. So that actually takes energy. It takes energy to overcome this interaction between any individual particle. When we free them, it takes energy to do that. We're giving them some potential energy to move around. So this equation only works when we're dealing with changes in temperature. It does not work during phase change. Luckily, however, there is a simple formula to deal with phase change. So during freezing / melting, the heat equation is the mass times heat of fusion. So this is heat energy mass and heat of fusion. Note, heat of fusion, you plug in a negative value. If it's freezing, we plug in a negative value if it's freezing, and we plug in a positive value if it's melting. By the way, negative heat, by definition, means heat leaving a system. Positive heat, by definition, is heat entering a system. So during freezing, we're pulling heat away to make it colder. So we should indicate it by a negative sign. When we're melting something, we're pumping heat into it to make it warmer. So we represent by a positive sign. During vaporization, which is a fancy word for boiling, our condensation, the opposite of boiling, The equation is heat is equal to mass times heat of vaporization. So heat energy this is mass. This is heat of vaporization. And heat of fusion and heat of vaporization and specific heat are just constants that depend on the material. You just look up in a table for whatever substance you're dealing with, and it will tell you the value for it. So let's work on an example. Let's do this example that we were just doing. How much heat, energy, is required to heat H2O from negative 10 degrees Celsius to 110 degrees Celsius? So our constants for H2O or water is Cp 4.184 joules per gram degree Celsius. H of F is equal to 334 joules per gram. And H of vaporization is 2,230 joules per gram. Again, drawing the graph. We're going from negative 10 degrees Celsius. Then we're going to melt it at 0 degrees Celsius. And then we're going to heat it up to 100 degrees Celsius. And then we're going to boil it. And we're going to heat it up to 110 degrees Celsius. Positive, not negative. So when the temperature is changing, so when we're going from negative 10 degrees Celsius ice to 0 degrees Celsius ice, we're going to use this equation. Q is equal to mass times Cp times change in temperature. Oh, and I left off some values. Specific heat. So this is Cp for solid. The Cp value for, this is for liquid. The Cp value for solid, so ice, is 2.04 joules per gram degree Celsius. And the Cp of H2O for a gas phase is 1.9996 joules per gram degree Celsius. So we're in the solid phase. When it's less than 0 degrees, it's a solid. So we have to use the specific heat value for when it's a solid. So I'll even put the S right here. So the heat would be the mass, and how much heat energy is required to heat let's do 500 grams. So we get 500 grams. So basically, we're starting out with a frozen bottle of water. Since it's a solid, we'd use 2.04 joules per gram degree Celsius. And the change in temperature, so we're increasing, so delta T is going to be a positive 10 degrees Celsius. We're going from negative 10 to 0. And so we get 10,200 joules. Alright, after this, we're going to go from 0 degrees Celsius ice to 0 degrees Celsius water. So this is going to be heat of fusion. So mass times the heat of fusion of water. So we have 500 grams times 334 joules per gram. And we see to melt all the ice, it's 167,000 joules. So relatively, it took way more energy to melt the ice than it took it to heat it up to the melting point. This is the reason why when it snowed, that snow took almost no time to reach the melting point. It didn't take much energy the day after to bring it up to 0 degrees Celsius. However, how long did it take for all the snow to melt? A long time. It was still here a few days later. Especially in the shadow portion where it's not receiving much energy from the sun. That's because it takes a lot of energy to actually convert it from ice to water. Then we're going to go from 0 degrees Celsius water to 100 degrees Celsius water. So we're not changing the phase yet, we're just bringing it to its boiling point. So we'll use the change in temperature formula. We will use the liquid CP of 4.184. So we have 500 grams times 4.184 joules per gram degree Celsius. And the change in temperature is 100 degrees. The energy required to do this is 209,200 joules. I want you to think about how close these numbers is. It only took a little bit more energy, relatively speaking, to heat water from 0 degrees to 100 degrees, so from the freezing point to boiling, as it did to actually melt all the ice. Which means if you're using an oven that's pumping out about the same amount of energy per second, if you took a giant big block of ice, it would take almost a little shorter than the time it would take to actually bring it up to boiling point. Now that we're at the boiling point, we're going to convert this between 100 degrees Celsius water to 100 degrees Celsius steam. How much energy do you think this is going to take?
One magnitude or less.
One magnitude less? One magnitude more? Alright. So you're thinking 2 million. A magnitude is when you add a zero or lose a zero. So one magnitude or less? So 2 million or 20,000? What you're thinking? That's a big range. That's two magnitude range going from 20,000 to 2 million. So mass times CP times delta. No. This is change in phase, so heat is equal to mass times heat of vaporization. So mass doesn't change, it's still 500 grams. Heat of vaporization is 2,230 joules per gram. So we get 1,115,000 joules of energy. This is why it takes so long to boil water. This is why if you put a pot of water on the stove and it starts boiling, when you get back, guaranteed the water's still boiling. You, unless you're gone for like like an hour or two or several hours, chances are you do not have you have not put enough energy to completely boil away all the water unless you start out with very little. It takes a lot of energy to actually boil 100% of that water. So if it took 1 hour to go from 0 degrees Celsius water to 100 degrees Celsius water, it would take 5 to 6 hours to completely boil it. So if it took maybe 45 minutes to melt a block of ice, an hour to heat it up to boiling point, take about 5 or 6 hours to actually boil it all the way. After this, we're going to go from 100 degrees Celsius steam to 110 degrees Celsius steam. So a temperature change. Since the temperature change, we use heat is equal to mass times CP times change temperature. Since it's gas, we'd use the gas value for CP, which is 1.9996 joules per gram degree Celsius. The change in temperature is 10 degrees Celsius. It's going from 100 to 110. And we see it takes less than 10,000 energy. Now then, the question says, how much energy does it take to go from negative 10 to 110? So the total heat would thus equal 10,200 joules plus 167,000 joules plus 209,200 joules plus 1,115,000 joules plus 9,998 joules. So in total, it would take 1,511,398 joules of energy if you started out with as ice and you're trying to boil it all away. Yes. This is why water doesn't freeze in winter. You can, unless it stays very cold for a very long time. Water has a very high heat capacity. It takes a lot of energy to change the temperature of water. And it takes a lot of energy to change the state of water, to make it go from liquid to solid or to go from liquid to gas. But if we look at this, almost 75% of the energy was simply converting it from liquid to gas. So if you're going from solid to liquid to gas, this phase for water is going to be the most energy intensive. That is because you're breaking all the bonds. You have to overcome all the bonds. You have to give it enough energy to overcome all the molecular bonds that's holding the water together. So CP for a solid or ice. So CP for ice is 2.04 joules per gram degree Celsius. Note these values again aren't necessarily constant. They change a little bit, but only a little bit based on temperature. But we'll assume they're constant. CP for water is 4.184 joules per gram degree Celsius. And the heat of fusion is 334 joules per gram. Suppose you have 500 grams of water. So you have your water bottle at room temperature, 20 degrees Celsius. And you place 100 grams, so a lot of ice, 100 grams of ice that's at negative 10 degrees Celsius. What is the final temperature and it'll be into the water? What is the final temperature after the system reaches equilibrium? So after the ice is melted and the entire drink has reached one temperature, it's no longer heating up or cooling off, what would be the final temperature after the system reaches equilibrium? So how would you solve it? So we're basically starting out with, on one side of the spectrum, we have negative 10 degrees Celsius ice, and we have 100 grams of ice. And the ice is going to heat up to 0 degrees Celsius and melt. And then the ice is going to reach some final temperature that I'll call X. Then we have 500 grams of water that starts out at 20 degrees Celsius and is going to cool off to some final temperature. And instead of calling it X, I'm going to call it TF for final temperature. The beauty of thermodynamics is we can treat these as separate entities. We can imagine it's the exact same scenario as if we took a block of ice and a glass of water and we just put them next to each other. Heat is going to flow from the hot liquid into the, so heat always flows from hot to cold. To solve this equation, we're going to need to do this. A new equation. Heat gained is equal to negative heat loss. So heat gained is equal to negative heat lost. Because these arrows are in opposite direction, they're going to have the same magnitude, but we need to flip them around, so we add this negative sign. Or I should say it's because heat losing has a negative, and we're going to need to flip them around. Hello? Sure will. No. He's supposed to be getting me a docking station. Bro, what'd you ask?
I said they still got you your desktop.
Nah, yeah, he's gonna give me a docking station to do instead for my laptop. So, let's break up this equal sign. So this is our main equation. What is gaining heat? What is getting hotter? The ice. So we're going to start with the ice. So we're going to go from negative 10 degrees Celsius ice to 0 degrees Celsius ice. Then we're going to go, we do arrow signs. Then we're going to go to 0 degrees Celsius water. Then we're going to go to some final temperature water. And on the right hand side of the equation, we're going from 20 degrees Celsius water to some final temperature. Note that to flip this equal sign, we need to add this negative. So here we're going to write out the equation. So this is heating up. So this portion of the heat would be mass of the ice times Cp of ice times the change in temperature of the ice. So this arrow right here represents that. Then we're going to add the heat of fusion, so mass of the ice times heat of fusion. This corresponds to this arrow. And then we're going to now be doing mass of the ice times Cp of water, because the ice is melted, times the new change in temperature here, and this corresponds to this arrow. And this is going to equal the negative of this arrow, which would be the mass of the water, times the Cp of water, times the change in temperature. Another way, one of the reasons why this negative here is because how I teach this class, this technically doesn't have to be a negative. But it's more better learned if you put the negative in and always remember that change in T is equal to final minus initial. If you're reading this left to right, it works out. If you always do this minus that, because this will be the initial minus final. So this is the initial temperature of the water. But if you do initial minus final, it's the same thing as multiplying by negative. And I think it works out better if you always do TF minus TI and add the negative sign to this. Does that make sense? Another way of looking at it is the sum. If I move this over to the left, the sum of all these values would thus equal 0. If I add this to both sides, this would be 0. So if you sum up all the arrows, there's no change in heat. Because none of the heat is leaving the system and none of the heat is entering the system. The system is after I mix them together. So I started out with 100 degrees Celsius ice, which would be 2.04 joules per gram degree Celsius. The change in temperature is 0 minus negative 10, so that's a positive 10 degrees Celsius. Heat of fusion, so 100 grams times 334 joules per gram. Now the water is melted, or the ice is melted, so it's 100 grams times 4.184. And we do final temperature minus initial temperature, which is 0 degrees Celsius. And that has to equal negative. Mass of the water was 500 grams. Cp of water is 4.184. And the change in temperature, let me actually just bring this down over here. So negative 500, negative 500 times 4.184 times, again, we'll do final minus initial. The initial temperature of the water on this side is 20 degrees. Now we have an unknown value and one variable. Now we just do algebra to solve for TF. So let me remove units because it gets troublesome to keep units in. Actually, for the first example, I'll keep the units. So gram, cancel out, degrees Celsius and degrees Celsius. So this is going to be joules. This is going to be joules. This would be joules per degree Celsius. So I end up with this right here is equal to 100 plus 2.4 and times. So we get 10,020.4 joules plus 100 times 334 joules. So 100 times that is 418.4 joules per degree Celsius times the final temperature. And that's equal to negative of 500. So 500 times 4.184 should be alright. Now we can add these together. So that's 43,420.4 joules plus 418.4 joules per degree Celsius times TF. I'm going to now distribute the negative and the 2092 into the equation. So that is negative, so boiling, negative 2092 into this, and negative 20 into that. Gives me 2092 joules per gram times TF. A negative and a negative becomes a positive. 4,184 joules. I highly recommend you do not keep units on this while working this out, as it's a lot to deal with. But at the same time, if you keep units into this equation, oh, and this should have been degrees Celsius. My bad. That should be degrees Celsius, and that should be degrees Celsius. I can help you spot mistakes. So, once we get into this equation, by the way, algebra skills, what do you do next?
Get the TF action.
Yes, get TF, collect terms. That's what we say in algebra. We want to collect terms. We want all the TFs on one side, all the constants on the other side. So I need to move this over here, and I need to move that over to the right side. So I'm going to add this over here. So 418.4 plus 2092 gives me 2,510.4 joules per degree Celsius times TF. Now equal moving this to this side, so I need to subtract it. Here's a mistake. I chose wrong values. Dang it. I always have to be careful when teaching this. This is an important lesson. Let me see, actually, go back to the very beginning and see if my calculator, if I can spot it. Because this shouldn't have been a mistake. I basically discovered that not all the ice will melt. And I did not want that scenario. I want to assume all the ices melt. No, okay. I found my mistake. Uh, What is 100 times 2.04 times 10? So this is basically 200 times 10, right? 100 times 2 is 200. 200 times 10 is what? Yes, that's my mistake. That should have been 2,040 joules, which means 2,000 plus that. So to illustrate why I knew I made a mistake, at this point, I got a negative value for temperature. If you put ice cubes into your water, would it freeze your entire water? So getting a negative value for water, so any negative value means the water is frozen. I realized my answer would be negative, hence the reason why I knew this was wrong. When I put ice cube into water, it should not freeze the water. This makes way more sense. And finally, I get a final answer. I still get a mistake. We'll work on this tomorrow. I'll find my mistake and work on it tomorrow. I swear, every time I teach this lesson, I think I can make up random values and I'll just assume that I don't make a mistake. I'm trying to teach this fast in one period. When doing this, Kobe, be careful, double check yourself. Where's my mistake?
Mr. West, check it out.
Yeah, fix the desk if you don't mind.
Oh, we're going over there again.
What did we do yesterday that I had
Lovely on.
We did a little thing that I put on Google Classroom for you.
Okay.
I'll give you a copy here in a second. So the mistake I made, Kobe, if you're watching this, is I forgot to multiply 100 by this number. I think. No, that's not the mistake. That does equal this. Alright. The correct answer should be 15 degrees. Where's the mistake I made?
What's up, man? Oh, you know, I think a beautiful day for granted. Ooh, numbers.
So this is correct.